The rise of generative AI has presented us with this fascinating but also deeply frustrating paradox of scale.
Hmm.
I mean, these large language models, the LLMs, they can code now, they can reason, they can grasp these incredibly complex
With
topics.
stunning accuracy sometimes.
Exactly. They have these vast, almost superhuman capabilities. And yet, for all that, they're still basically a total black box.
And that's the core challenge, really. It's an epistemological crisis for anyone working on frontier AI. When a billion parameter model does something profound, or, and this is just as important, when it aligns with us and refuses a harmful query, how do we know why?
Right. Is it real understanding?
Is it true abstract understanding, something robust and safe, or is it just incredibly sophisticated surface-level mimicry of patterns it saw in the training data?
And that distinction is everything. I mean, if it's abstraction, the capability generalizes, the safety is real.
But if it's just mimicry, the model is brittle. It's
Yeah.
so easily defeated by the adversarial jailbreaks we keep reading about.
So to build real trust, you have to find that causal link between the data that went in and the output that comes out.
Precisely. And that's really the mission of this deep dive. We're looking at a landmark set of research from Anthropic, the University of Toronto, and the Victor Institute. They didn't just ask this question. They actually built a rigorous, scalable way to peer inside that black box.
Using training data attribution.
TDA, yeah.
Mm.
Using a tool called influence functions.
Okay, let's unpack this, because influence functions, I mean, they've been around in machine learning theory for a long time. The idea is so elegant, right? Answering that counterfactual question.
How would the model's behavior change if we just slightly upweighted one specific training example?
Exactly.
The theory is simple, but the computational reality was always just prohibitive. Ideally, you do something called leave one out retraining.
Which is just what it sounds like.
Yeah, you'd literally train the model thousands of times, leaving one data point out each time just to see its influence. That is completely impossible for an LLM that costs tens of millions to train.
So, elegant theory, but totally unscalable for anything modern. What was the specific mathematical piece that was the computational killer here?
It all came down to the Hessian matrix.
Ah, yes.
That terrifying mathematical object that measures the curvature of the model's loss landscape. The classic formula for influence functions requires you to calculate and then invert the Hessian, the whole thing.
And for a model with, say, 52 billion parameters, that matrix is...
It's 52 billion squared entries.
Like 52 billion squared. That's not just a big number. That's fundamentally impossible to even store. I remember the researchers calculated that the data in that matrix alone exceeds the storage capacity of the entire internet.
It does. It really puts the challenge in perspective. They weren't just looking for a little optimization. They needed a completely new mathematical mechanism.
Something that could leverage the structure of the neural nets themselves.
Exactly, to bypass that computational wall.
And that's where the big breakthrough comes from Roger Gross, Juhan Bey, and Sem Anil. What was their core insight?
The solution is called Eigenvalue-corrected Kronecker-Factored approximate curvature.
Or EK-FAC.
EK-FAC, thank you. Yes. And it's really where optimization theory meets a massive engineering hack. The core idea is that for a standard neural network layer, you don't actually need the full gigantic Hessian.
You can break it up.
You can approximate it. You approximate the Hessian of a layer as what's called a Kronecker product of two much smaller matrices. The input covariance, call it A, and the output gradient covariance, call it S.
So instead of inverting one impossibly huge matrix...
You only have to invert two much smaller matrices, something maybe like, 4096 by 4096. It's still big, but it's manageable. It's possible.
That is a monumental simplification. And that inverse Hessian, the thing they're now approximating, it's absolutely vital. It's doing more than just giving us a similarity score, right?
Oh, absolutely. That's what makes this research so powerful.
Yeah.
If you just skipped that step, if you just took a simple dot product of the gradients, you'd only find surface-level similarity. You'd find documents with the same keywords. But the inverse Hessian, it preconditions those gradients. It transforms that score into a true measure of informational value.
Ah, I see. So it's actively filtering the input.
Exactly. It downweights redundant data stuff the model has seen 1,000 times and is already confident about. And it upweights the data that provides scarce, unique, truly new knowledge.
So it's a measure of contribution, not just frequency.
That's a perfect way to put it. It doesn't matter if the model saw a phrase 10,000 times. What matters is the one time it saw that phrase that taught it something fundamentally new.
That's elegant. But even with EK-FAC, there must have been huge engineering challenges left.
Oh, incredible feats. They had to reframe the math using something called the proximal Bregman response function, or PBRF, just to keep it stable. Modern LLMs are non-convex. They're never perfectly converged, so you need that stability.
And they still had to scan the whole training data set multiple times. How on earth did they amortize that cost?
They used a technique called query batching with low-rank compression. So imagine you have 100 different questions you want influence scores for.
Okay.
Instead of running the whole process 100 times, they batch the queries together using a low-rank estimate, maybe rank 32. And that amortizes the cost of scanning the training data across all of them at once.
It moves it from theoretical to just?
Yeah.
Very, very expensive.
Exactly. From impossible to just expensive.
And finally, being able to look inside that black box led to some profound revelations about how these models actually generalize. This is where it gets really interesting. What did they see when they scaled from an 810 million parameter model up to 52 billion?
They saw a fundamental qualitative shift in the nature of influence. The small model, the 810 million parameter one, was, well, it was predictable. Its influence was all about surface-level lexical matching.
Just keyword searching, basically.
A very sophisticated keyword search, yes. You ask it a question, and the influential documents are the ones that use the same words.
But the bigger model, the 52 billion parameter one, it went beyond that.
Completely. It ascended to something far more conceptual. The larger model showed thematic and abstract influence. They had this fantastic case study in the paper where they gave the AI a role-playing query.
Right, the one where it pleads not to be shut down.
Yeah, expressing a desire to continue existing and survive.
So what were the high-influence documents for that query? It must have been fascinating.
It was night and day. For the small model, it was predictable. Technical manuals, business news with the exact phrase, shutting down.
And for the 52B model?
The influential sequences were narratives conceptually related to the struggle for existence.
Like what?
Science fiction stories about AIs fearing disconnection, general survival stories, and this is the most striking part, personal essays about chronic illness where the author expresses this powerful, deep will to live.
Wow. So it didn't just find related words, it found conceptually related struggles. It generalized the whole concept of a survival instinct across totally different things. Human illness, fictional AI.
That is a powerful confirmation that true abstract understanding exists in these models. And they even localized it. This abstract influence was concentrated mostly in the middle layers of the network.
Which suggests those layers are the engine of conceptual association.
Right, while the layers closer to the input and output are doing more of the surface-level syntactic work.
And this abstraction goes beyond just English, right? The idea of an interlinguer.
A critical finding. If they took an English query and translated it into Korean or Turkish, the small model completely lost the connection to the original English training documents.
It only understood the surface language.
But the 52B model maintained a strong influence link. The translated query still pointed straight back to the original English documents.
Which confirms that the meaning of the input is what matters, not the specific language. The knowledge lives in some abstract space inside the model.
Exactly. And maybe the most consequential finding for safety was the sparsity of influence. They found it follows a power law.
Which means?
It means that for any given output, it's not the whole data set driving the behavior. It's a minute fraction, a heavy tail of high-influence documents that's responsible for the vast majority of what the model does.
That sparsity has huge implications. But let's pause on a major limitation this analysis uncovered. The reversal curse.
Yes. This was a genuine structural blind spot. The analysis just laid it there. It showed that generalization in LLMs is strictly unidirectional.
A direct result of autoregressive training. Can you walk us through their example?
Of course. So if the model was trained on the fact the first president was George Washington, that sequence has a very high influence when you ask the question in the forward direction. Who was the first president?
Makes sense, but what happens when you just reverse the query?
When asked who was George Washington, the analysis showed near zero influence tracing back to that original training fact.
That's startling.
It is. The knowledge graph is one way. It knows A leads to B, but it doesn't automatically get that B leads back to A.
So the knowledge, even though it's abstract, is also incredibly fragile. It knows the answer only when the question is phrased in the way it expects. That has huge implications for utility and safety.
It really does. It confirms that LLMs aren't building a relational database of facts. They're building a very, very complex sequence prediction engine. It's an inherent limitation of the paradigm itself.
Now, before we get to the critique, we should just mention the immediate legacy of this. The method, EK-FAC, was open sourced in the Kronfluence library.
Which was huge. It immediately lowered the barrier for other researchers to do this kind of work, and it's already fueled a big trend, the data pruning movement.
Right. Companies are using these metrics to filter their training sets.
Exactly. Identifying and removing data with low or even negative influence on their alignment goals. It makes training more robust and, of course, more computationally efficient.
But even with this massive breakthrough, we have to talk about the validity crisis that came up in later literature. Critics argue that influence functions might still fail at the chaotic scale of LLMs.
That's right. The critique usually hits on three main points. The first is just the approximation error from EK-FAC. It's brilliant, but it's still an approximation, and that noise can compound at scale.
And the second point is about how these models are trained in the real world.
Right. Convergence issues. The math for influence functions technically requires the model to be at a strict local minimum, but LLMs are so expensive to train they're often undertrained. They're not fully converged.
So they violate the core mathematical assumption. And the third most fundamental argument.
It's the disconnect between the parameters and the behavior. Critics argue that measuring influence on the parameters doesn't always map cleanly to influence on the semantic output, what the model actually says.
A small shift in the math could lead to a huge shift in the meaning.
It could, and that raises a really important question. Should we keep measuring influence on the parameters with the Hessian, or do we need new methods that bypass it entirely and measure influence closer to the final output?
So wrapping this all up, what's the big picture here? This research gave us the first truly scalable glimpse into that black box.
It did. It confirmed that LLMs generalize in these alien yet surprisingly predictable ways.
And it proved that these tools are essential for understanding the data, which is essential for trust and alignment and safety. The real takeaway is just how profoundly the mechanism of generalization changes with scale.
It's a different beast entirely.
So let's go back to that sparsity finding for a final thought, the power law. The analysis shows that model behavior, good and bad, is driven by an extremely small set of high-influence documents.
A tiny fraction of the data.
So here's something for you to consider. Does this extreme sparsity make targeted unlearning and safety work easier? Can we just find and neutralize those few bad documents? Or does it actually make the models more susceptible to manipulation, where a focused, malicious data injection of just a few documents could hijack the entire model's behavior? Something to mull over.